Okay, now let's talk about the radial basis function networks. So this one is a linear regression with the radial basis functions. Okay. Again, the basis functions are radial or Gaussian canons. So we already talked about all the equations about these radial basis functions. Okay. So given the data, then we have lots of basis functions, and approximation is based on the weighted sum of these basis functions. Okay, and the radial basis function network is actually a linear regression, but at the same time it is a kind of feed for neural networks with one hidden layer. And in the one hidden layer, the first layer is not trainable. Okay, we just provide the basis functions, and these basis functions are fixed. Okay, and then the output layer with the parameter w is trainable. And it looks like this, first of all. So the hidden layer does nonlinear transformations. So from input x, so we apply the nonlinear functions so that we have hidden layer representation. Okay, and this layer is fixed. Okay, the nonlinear function is given. And then from these features, then we multiply this parameter vector to get the output. When we have a multivariate output, then we might have a lot of output nodes. But if we have just a scalar, then we have only one output. Okay, then usually higher dimensional space than the input space. So when the input vector is in the d-dimensional space, then in this hidden representation, we have m nodes, and m is higher than d usually. But sometimes we can have a smaller dimensional space, but usually higher. And each hidden neuron responds to a local region of feature space. Okay, so we already talked about this local property of Gaussian function, right? So Gaussian basis function or radial basis function are local. Okay, so one basis function is in charge of some local locations. Okay. So to match the data distribution, then clustering could be applied. Okay, so if you want, you can use clustering, but it's not necessary. Okay, so the linear output layer does linear regression. So this part will take care of nonlinear transformation, and then this part will be just a linear regression. Okay, and this one is trainable. Okay, but this neural network, again, this one is a neural network actually, in a sense, and this one is much faster than multi-layer perceptron. In the multi-layer perceptron, this part is trainable too, and this part is trainable, so we have two trainable layers so that it is hard to train multi-layer perceptron. But in radial basis function networks, this part is given. So when we have input x, then we can translate the x to these hidden representations. Okay, then because this one is fixed. And we can train just this layer. So it's just a linear regression. It's really fast. So to train these RBF networks, it takes just it doesn't take much time. It takes less than 1 second. Okay, even when you have a lot of data samples, but still just less than 1 second would be enough most of the time. And the number of bases and number of parameters, these are hyperparameters, right? And the larger they are, the more flexible the function is. But If we increase the number of pages and the number of parameters, then there is some possibility. We increase the kind of the probability to have overfitting problem, as always. And the RBF network's algorithm is really simple. So define the basis functions first. So we have to define the means and variance because RBF is Gaussian functions. Okay, so we have to define means and variances. And if you want, you can use a clustering method to have some basis functions where there are lots of data samples. So we can have a basis functions where there are data samples. So for example, we have this kind of data samples. Then we can have radial basis functions around here. So in that case, maybe 3 basis functions would be enough to represent all the data samples. But usually we don't do this. We use grid approach. We have lots of basis functions like this. We can manually define with lattice and prior knowledge for the variance. So we can just predefine these things. Or if you want, you can use clustering method. And then now we have a basis function matrix, right? Because we just define the basis functions. And then given these data samples, just apply these basis functions. Now we have basis function matrix. Then to learn the weight matrix. When we have multiple outputs, then the weight would be a matrix. If we have just one output variable, then W can be just a vector. Okay, then simply use a pseudo inverse. That's it. Okay. Then we can predict the output of test data. And there is a major drawback of RBF networks. RBF centers are not guided by the MSE objective functions. In the previous slide, when we define these basis functions, okay, these basis functions are defined regardless of the objective functions. But in the deep learnings, all the layers are kind of organized to optimize one single objective function. But in RBF networks, the basis functions has nothing to do with the objective functions, right? We just simply define. Even when we use a clustering method, then still this clustering method has nothing to do with the objective functions. So that is one big problem. And we have some nice examples. The first one is a circle in the square. In this square, we have a circle. And we have a lot of samples. And based on these samples, we have to estimate these circles. Okay. If we increase the number of samples, then we can increase the number of basis functions. Then this estimate would be close to the actual circle. And we have another example, function approximations. So the blue curve is the predicted curve, and the dotted red curve are just the data samples. Okay, from these data samples, we just estimate our estimated function is this blue curve. Okay, so with just the 20 samples, we can estimate this function, and the MSE is quite low. But if we increase the number of samples, then we can increase the number of basis functions. Then the MSE would be almost 0. So in this case, where is the basis functions? We have basis functions like this. But if we when we don't have enough samples, then the basis function should be big, okay, to avoid overfitting problem. And the next one is kernel approach for linear regression. So this one is a straightforward application of kernel trick to linear regression when we use nonlinear function phi. So please refresh your memory about the kernel PCA. So it's quite similar to kernel PCA. So we're gonna do a linear regression after applying a nonlinear function phi on input x. Okay, then this is our loss functions. This one is about the regularizations, so you don't have to worry about this part yet. Okay, so after after learning regularizer, then we can get back to this term. But for now, just ignore that. And with this equation, I think we already talked about this term, this equation, when we derive the kernel PCA, right? So W can be represented by a weighted sum of a nonlinear function phi, okay? Because W should be in the same space. So in this case, we have a weight W in the feature space. Okay, so as long as W is in the feature space, then the W could be represented by the weighted sum of feature vector. Linear regression can be a dual representation. So just simply use this term in place of W here. Then we can simply have this term. Again, this term, you can just ignore this term for now, okay? Then, you know how to apply the kernel trick, right? So whenever there is inner product between the feature vector or between the input vectors, then we can use kernel function instead of nonlinear function and the inner product. We can just use a kernel function. So with these kernel functions, then this inner product can be replaced by this kernel. So our objective function can be rewritten with this term. Again, this one is regularization term. So for now, you can just ignore that. Okay, then take a derivative and set it to 0. Then alpha is, without this term, alpha is k inverse t. So given a new point x, then y of x is double transpose phi of x. Okay, so this one is exactly same as kernel PCA. When we have a mapping, then given a new data point, then we could project the new sample to the y space, right? So likewise, exactly, we can apply the same equation. So double transpose phi of x can be rewritten like this. Then there is inner product here. So we can get this result.